A modern commercial facility hides a massive, interconnected nervous system. It's a dense network of HVAC, plumbing, and drainage infrastructure operating continuously. These combined networks represent a substantial portion of a property's capital investment, driving its largest operating expenses. Yet a structural paradox exists in facility management. Commercial operators spend millions annually on preventative maintenance contracts and still experience unpredictable equipment breakdowns, tenant disruptions, and escalating utility costs. Treating these complex networks as static items on a routine maintenance schedule fails to protect the facility's bottom line or its operational continuity. The root of this failure is a widespread industry practice we can call the checklist illusion. Conventional programs prioritize task completion. A technician signs a form and leaves. Executing a checklist isn't actual diagnostic verification. Checking a box on a pristine piece of paper creates false security, rarely revealing if equipment is operating as originally designed. This gap in oversight leads directly to a condition known as performance drift. Mechanical systems almost never fail instantaneously. Instead, they gradually degrade over time. Airflow becomes restricted, heat transfer surfaces accumulate dirt, and electrical components lose efficiency. Because the unit still powers on and cycles air, this slow degradation is completely invisible to a standard routine inspection. The machine is running, so the technician checks the box. Left unchecked, this drift surfaces elsewhere on the balance sheet. It manifests as consistently higher energy consumption, more frequent service calls, and equipment that burns out years before its intended lifespan. Checklist-based maintenance only manages the most superficial symptoms of operation, while allowing deep, hidden stressors to multiply out of sight. To see exactly how drift bypasses standard visual inspections, look at a standard commercial rooftop HVAC economizer. When operating properly, an economizer pulls in cool outside air when environmental conditions are right, reducing the mechanical load on the compressors and significantly lowering cooling costs. This exploded diagram shows the internal mechanics of a rooftop unit. A basic visual check misses critical failures deep inside. You find sensor drift, misaligned control sequences, and worn actuators. This compromised logic forces the system to run energy-intensive compressors for unnecessary cooling cycles. The financial consequence is a massive amount of hidden energy waste that compounds quietly, month over month, completely unnoticed. Verifying that an HVAC unit has power and a clean filter is useless if its internal operating sequence is actively sabotaging your facility's energy efficiency. This dynamic is even more pronounced in plumbing and sewer infrastructure, where the prevailing management culture is almost entirely reactive. You fix what breaks exactly when it breaks. But mechanical drift applies to water systems too. It surfaces as a slow, quiet deterioration of baseline performance. This illustration shows the compounding nature of neglected commercial pipe networks. Minor, undetected leaks and pressure irregularities accelerate mechanical wear. Sediment destroys heat transfer efficiency in water heaters. In drainage lines, grease buildups mature into calcified obstructions, setting up an inevitable chain reaction of failure. These ignored baseline conditions guarantee that the facility will eventually experience catastrophic, highly disruptive downstream events, like widespread pipe failure or severe sewer backups. Waiting for a pipe to burst or a drain to back up before taking action means you are managing a catastrophe. You are no longer managing an asset. Counteracting this degradation requires moving from reactive maintenance to a proactive model known as mechanical stewardship. This is executed through a disciplined 4-phase framework. This chart tracks system performance. Standard preventative maintenance fails to keep equipment in the optimal zone, resulting in a steady downward curve. You cannot maintain poorly operating equipment. That brings us to Phase 1, restore. Systems must be rapidly restored to a healthy baseline. This requires technicians to actively identify accumulated deficiencies, clear hidden airflow and heat transfer restrictions, and execute years of deferred repairs. You have to bring the asset back to a state of baseline mechanical health before routine maintenance can actually be effective. Once the baseline is reestablished, the framework moves to Phase 2, stabilize. Stabilization abandons static checklists. Instead, technicians use active diagnostic monitoring to verify pressures, track electrical load, and catch early signs of imbalance before they force a complete mechanical breakdown. With the system stabilized, it enters Phase 3, Optimize. At this stage, technicians execute targeted refinements. They align control sequences, maximize heat transfer efficiency, and balance airflow, pushing the equipment to its absolute maximum operational efficiency. Phase 1 repairs the machine. Phases 2 and 3 actively guard against the return of performance drift and securely lock in your energy savings over time. At this point, the physical work in the field begins to generate high-level value for the boardroom, moving from mechanical repair to financial forecasting. This is the ultimate goal of mechanical stewardship. Phase 4. Plan. The diagnostic field data gathered during stabilization and optimization is compiled. It transforms from raw mechanical health scores into a clear, reliable 5-year budget timeline. This visibility gives facility leaders the data to accurately anticipate system life cycles and prioritize capital expenditure without guesswork. Funding a scheduled equipment replacement during the off-season is drastically cheaper than paying the massive emergency premium for an unplanned midwinter failure. This framework delivers distinct, verifiable results in the field. Consider a recent deployment for a national retail client managing 9 separate locations. Ahead of peak winter demand, a proactive restore phase protocol was executed across their entire portfolio to correct existing deficiencies. The result was definitive. Across all 9 managed sites, the client recorded exactly 0 emergency no-heat calls throughout the entire winter season. That level of operational predictability is impossible to achieve when relying on a reactive, checklist-based model. The risk is only compounded when facilities use fragmented vendors. Spreading HVAC, plumbing, and drainage contracts across multiple companies blurs accountability and ensures that systemic problems are ignored. A single partner accountability model eliminates the finger-pointing. It unifies oversight, ensuring that every piece of critical infrastructure is managed under one cohesive standard. Abandoning the checklist illusion and committing to mechanical stewardship lets operators step out of the break-fix cycle. They transform their mechanical networks from unpredictable liabilities into reliable, high-performing, long-term assets.